Okay. So, Andrew, over to you.
All right, thank you, David. Yeah, and thank you for the invitation. It's lovely to be able to talk at such a distance and to have everyone so familiar with it by this point. And so, yeah, I'm currently sitting at -30 Celsius. So I've picked an appropriate background for the Zoom call up here in Northern Canada. And I'm going to talk today about, it's going to be sort of a long story, but a lot of survey at the beginning to sort of set up where my mind currently is in my research. Starting with an old problem, which is a problem about what are called quantum subgroups. Okay. And so as a small outline, I'm going to start talking about, happily enough, a resolution of a certain problem about quantum subgroups as a way of setting up all of the characters in the story that I'm going to tell. And I'll take about 2 slides to do that. And then I'll talk more about why I was interested in that problem and some devices that came along the way while I was working on it. And I'll take about 5 slides for that. And then time bearing, we'll see how much I can talk about this sort of new set of ideas that's in my head about what I call Galwan Variants and some science fiction, some stuff that isn't completely rigorous yet, but I think is going to be quite interesting. And I'm not going to give a number of slides for that because who knows how far we'll get into. So our story starts in a mathematically physical place, which is rational conformal field theory, which has a mathematical realization as rational vertex operator algebras, which I have slowly been learning the language of. This is kind of my second language, if you will. I came to Canada the first time about 3 years ago, and I learned that everyone talks in the language of VOAs here. And so I've slowly had to incorporate these words into my vocabulary. So if my grammar isn't completely correct, please be slightly forgiving for that. So I'll label this very shortly as RVOA, the few times that I actually have to refer to them, and they're going to look like the letter V. Now, the language that I'm more familiar with is when we look at categories of modules over these rational vertex operator algebras, this beautiful result is that they form this incredibly highly structured category called a modular tensor category. So modular tensor categories, I'll abbreviate as well and give them slightly italicized C to represent them. These are the language that I'm more familiar with, the language that I was raised on, so to speak. And so these two worlds talk to each other a lot, and there's a lot of communication between them. So the main structure that I like to study in these things in the VOA side, I hear, is called extensions. Okay, so one rational vertex operator algebra sitting inside of another. And these extensions on the modular tensor category side take the form of algebras. And so I have a commutative algebra object inside of my modular tensor category, and I can, with sufficient number of adjectives, which I've represented with a plus here, with a sufficient number of adjectives, the category of local modules over this algebra forms a new modular tensor category. And the details of that are unimportant to what I'm going to discuss, but this is roughly the connection between these two worlds. Now, the hardest part about this translation, at least for me, and I'll call this whole story quantum subgroups. And quantum subgroups, I've noticed, has been coerced to mean lots of slightly different things. some people refer to this in a much grander sense, these quantum subgroups. But in this talk, this is exactly what I'm talking about, these extensions of rational vertex operator algebras and the existence of these algebra objects in modular tensor categories. So the hardest part about this translation for me is that this is what's happening in my head when I'm thinking about them, is that in VOA land, you're extending, you're sort of going in an upward direction. Except in the category land, you're going down, okay? So these categories are becoming smaller as you apply this operation of taking a category, looking at local modules over it, you're decreasing the size of the thing that you're looking at. So there's this sort of inverse relationship. So whenever anyone talks about the VOA side, I sort of have to stand on my head to understand what they're talking about. So this is roughly the world that we're going to be living in for some of this talk. Now, the canonical example of these, which are incredibly deep in the results that you can find about them, are related to this WZNW model, or sometimes WZW model, I believe that people also call it in the conformal field theory language, which for the VOA, the ingredients start with some affine Lie algebra. So I take some, let's say, simple complex Lie algebra G, and I look at the affine Lie algebra corresponding to it. And if I want to create this modular tensor category, I can look at positive integer level representations of this, this affine Lie algebra, and get a modular tensor category, which I'll call C, which is roughly the category corresponding to that simple Lie algebra and that positive integer level. And so the extension side of things, or the quantum subgroups side of these categories, is what has been interesting, at least in the beginning of my research. So these extensions come in two different flavors. So I have what I'm told are called simple current extensions, which are sort of the easiest extensions to understand. And then I have everything else, which I'll call exceptional extensions. And in the category side, these correspond to algebra objects, which come inside of Tanakian subcategories. So these are finite group-like algebras. And any other algebra that you happen to come across, we'll just call exceptional. And so the long-standing conjecture was that if I fix a simple Lie algebra, then there exists some positive integer bound such that if I look at these categories at levels past that bound, then I'm not going to find anything out of the ordinary. I'm not going to find any exceptional quantum subgroups in these categories. So all of the interesting stuff that I find past that point will be group theoretical in the modular tensor category language, or there'll be simple current extensions in the VOA language. And this problem was resolved in some language in, let's see, that was probably the late 80s. So about 30 or more years ago at this point. And I apologize, I'm not going to list any names just in the interest of time, but there's tons of names that are associated to this that I can give you a list of afterward if you'd like. And so this was done for A1, this was done for SL2 30 plus years ago. And then the guy that I work for now, Cannon, in the language of modular invariants, sort of settled this problem for SL3 for A2 about 30 years ago. And then there was this long period where there were murmurings of how to proceed with this problem. And in fact, there were some sentences, very small number of sentences written down about how you could proceed to solve this sort of problem. And in some ways, they were very accurate these sentences that were written down about how to solve this problem, but no one did it very explicitly. So for instance, for any other algebra, there was no proof, not even sort of rigorous evidence that, that this bound was tight for any other algebra. And so one thing that I did, and I write my surname here in its full, so people learn how to spell it. One thing that I did very early was to actually prove this level bound exists, give an explicit bound for the rest of the rank 2 Lie algebras, and sort of give a general way of how, if you had enough time on your hands, you could do this for the rest of the Lie algebras. So I told this to Terry Gannon, and he said, well, that's great, well, then we'll do that. And so if you Google Gannon, he gave a talk in Banff at Burse in October 19th of 2018, which basically describes this proof for just all Lie algebras. And so that sort of put a resolve to this problem. So now, for any fixed Lie algebra, you can get an explicit bound, and it's quite a nice bound. My bounds for rank 2 were, they were horrible. History will not be very forgiving for how bad my bounds are, but the bounds now are around, I think, the rank of the Lie algebra cubed in general, or something like that. So this problem has a very nice resolution. And it's great because this sort of sets up the stage for what my main research project has been since then, which is studying a much larger problem than these quantum subgroups, which is that if I look at all modular tensor categories, or even more generally, non-degenerately braided fusion categories, I want to know how are all of them related by quantum subgroups. So more specifically, I want to know that if I have this process of taking an algebra and looking at category of local modules, I want to know when can I apply this process to 2 different categories and get sort of a common ancestor along this process. Okay? So this actually forms an equivalence amongst modular tensor categories, or non-degenerately braided tensor categories, which we call Witt equivalence. So this is actually an equivalence relation. So essentially, I'm asking, the big question is to ask, how can I organize all of these categories into little piles which are equivalent? And in fact, if I look at these equivalence classes as a set, then they have a nice group structure. Since I can tensor 2 of these categories together, I can also tensor 2 of these equivalence classes together to get a new one. Okay? So it's slightly irrelevant to our story, but there's this nice group structure, and that's been the focus of why I've been studying these quantum subgroups. So the rough recipe for classifying these relations, so say someone gives you a specific pile of categories, maybe the categories that correspond to SL2 in the WZW case, and they want to know how to organize the class. Well, a very rough recipe, modulo some details, is the first thing I do is I solve this quantum subgroup problem. First thing I have to know is I have to know every single quantum subgroup in every single one of these categories that I've been given. So once I know that, I can look at the categories of local modules, and I can pass to a representative of that class that is up to equivalence the smallest. And then I want to factor all of those sort of boiled down versions of my categories into prime factors. Okay. So first I take all my categories and I make them as small as possible, and then I factor them to make them even smaller in a different way. And then I have all of my little ingredients and I just have to differentiate them, not in a calculus way. I'm teaching calculus right now, so I should be accurate. Not differentiating them in that way. I'm actually just trying to distinguish. Distinguish might be a better term. I want to distinguish all of these little prime factors. So you can follow this recipe for any set of categories. Originally, it was done when these concepts were devised for the rank 1 Lie algebra, so for SL2, in the second paper that was written about these Witt group relations. And then with my understanding of these quantum subgroups, I went ahead and did it for the rank 2 Lie algebras for A2, B2, and G2, which the whole process took 2 different papers to get through all of these different steps. So there's this huge problem, which is very time consuming and has a lot of multiple steps. And surprisingly, at each given step along the way, the arguments sort of seem to boil down to one thing. And so from this huge problem, it seems that I've needed to understand very specific things about these categories. So the linchpin, so the thing that is tying all of these arguments together, has been modular data, which is associated to these categories. So that's not surprising. You know, the modular data is a crucial part of these categories, but we can be even more specific than that. So more generally, what one wants to understand is numerical invariants, which are associated to fusion. So we have this tensor structure on the category, and we want to understand numbers, specific numbers, but also fields of numbers that are associated to these structures. So just a very rough outline. So this modular data comes from the fact that if I have a modular tensor category, I can associate to it a representation of SL2Z, this modular group. And the size of that representation is exactly the rank of the category. So the number of isomorphism classes of simple objects. So typically on these canonical generators of SL2, which we call S and T, we call these matrices S and T, obviously with a slightly different font. So this S matrix is a rank C by rank C symmetric matrix indexed by the simple objects. And the T matrix is actually diagonal, consisting of roots of unity, which correspond to the simple objects of the category. So these are very explicit things that you can compute. So rather than studying the modular group representation, the true representation, sometimes we consider this unnormalized form. So the capital S and the capital T that I'll talk about, these are actually more standard in a lot of people's papers, depending on what you're studying. And these give a projective representation of SL2Z, but in a lot of ways, from a number theoretical perspective, sometimes they're easier to study. So when I talk about S and T, I'm typically talking about capital S and capital T, if it were. And so one of the nicest thing about this modular data, which has been known since sort of the beginning of all of this study, is that if I look at the characters of the Grothendieck ring, so the characters of the skeleton of this modular tensor category, then they're given by this modular data. So they're given by these ratios of entries of the S matrix. So since these two different versions of the modular data only differ by a scalar. In these ratios, we have the exact same result. So it doesn't matter which S and T matrices I'm referring to in this case. So this is sort of the underpinning of this entire story. So in honor of Verlinda, I'm going to call the set of all of these ratios of these S matrix entries the Verlinda eigenvalues. So when I was explicitly trying to solve these problems, you know, I was a graduate student and I had just learned what, well, 2 years ago, I just learned what a category was. And then now I'm studying these modular tensor categories, and I didn't have a perspective of the entire picture of what I could use to solve these problems. And so I looked at just one row, or in general, it could be one or two rows or columns of these S matrix, which correspond to dimensions. So there's two different concepts of dimension, which for people who study unitary things, these are the exact same measurements. One is the values of which we call Frobenius-Perron dimensions, named after the fact that we're using Frobenius-Perron eigenvalues of matrices to measure them. And this gives a character of the Grothendieck ring. And on the other side, we also have what we call categorical dimensions. So we're looking at traces of the identity endomorphisms on simple objects in the category, which are sometimes very different than the Frobenius-Perron dimensions, depending on what category we're looking at. And this also gives a character of the Grothendieck ring for these modular tensor categories. So these are a very nice thing to look at, but you're really only looking at a tiny piece of the picture, a tiny piece of the modular data. So if you have this rank 100 modular tensor category, really you're using 1/100th of the information that's available to you from the modular data by looking at these dimensions. And amazingly, even looking at a tiny, tiny percentage of the data that's available, this is enough to make very complex arguments about these categories. So essentially, if you look through all that it took to prove these bounds, you'll find that the main tool, really the thing that takes up the guts of all the arguments, is just dimensions, 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 dimensions. And if you look at a lot of other papers, you'll find that this is also the case. If I want to look at, for instance, automorphisms of these categories, really the first thing that people go to is to look at dimensions. Automorphisms have to preserve dimensions, and so this is essentially the very first and largest tool that I use to study these. So it's just pervasive through the entire literature that you need to understand dimensions to understand the categories. And I was surprised to find that our knowledge of these things, our knowledge of these concepts, is very sporadic. So you can't sort of put it under one umbrella, all of the facts that we understand about these dimensions. So this is a little biased, but here's a very small list of things that we know about these dimensions. One is they're cyclotomic integers, which is very nice from a number-theoretic perspective. We also know very random facts, like one thing dividing another. So when I say dimension of a category, I just mean the sums of squares of the dimensions of the simple objects in either form. So we know that the dimensions of the simple objects divide the dimension of the category in one way or another. We know how these two dimensions divide one another, the Frobenius-Perron and the global dimension. We know that the set of all Frobenius-Perron dimensions of these modular tensor categories, or more generally fusion categories, is a discrete subset of the real numbers. We know that categorical dimensions of simple objects are very, very, very special types of cyclotomic integers, which are called D numbers, which is a number which has this nice Galwan variance property. We know that there's sort of a Lagrange theorem for Frobenius-Perron dimensions, which says that if I have a fusion subcategory, then its Frobenius-Perron dimension divides the Frobenius-Perron dimension of the big category. We know that the categorical dimensions of simple objects are totally real. And for instance, the categorical and Frobenius-Perron dimensions of the category are totally greater than or equal to 1. So all of their Galois conjugates are positive real numbers to the right of 1. So if you look at this list, which obviously isn't randomly generated, how do you classify all these facts together? They seem sort of random. In fact, I gave a talk in the Netherlands in a number theory seminar, trying to garner some interest in these types of numbers that appear out of these categories. And someone off the books who doesn't know that I'm telling this story right now, they said, you know, your area of research really has no idea what's going on, do they? Because these numbers, we have no idea what types of numbers are appearing. We know lots of specific facts about these numbers, but no big general picture, no nice characterization or anything like that. So rather than trying to just shoehorn all of these random facts that we know about these types of numbers into fancier and fancier arguments, I thought it would be nice to look at these numbers and try to find out more uniform facts about them. And it's actually quite difficult. So this is a very active topic. There's lots of open space for study. So for instance, even within the past couple of years, there was a couple of results in this area, actually lots of results. This is a small list of them. For instance, with these categorical dimensions of these categories, we don't even know if this is a discrete subset of the real numbers or not. But Victor Oestrich managed to prove that at least one point in the real numbers is not a limit point of these categorical dimensions, which is the smallest possible categorical dimension, which is 1. And in the same paper, he proved that if you fix a global dimension, then there are finitely many fusion categories which realize that global dimension. And I sort of took that a little bit further and proved that even if you fix an algebraic norm, so you take all the Galois conjugates of these cyclotomic numbers which represent categorical dimension, multiply all of them together, and you get an integer, a positive integer. Even if you just fix that integer, there's only finitely many modular tensor categories with that algebraic norm of the global dimension up to equivalence. So that's a very strong restriction. And very surprisingly, this Lagrange theorem for categorical dimensions hadn't even been proved yet until last year. It's something that a lot of people, I think, thought was true and maybe even thought they could find a reference for it. But the first time that it appeared in the literature, I believe, was last year. So we're still making very small elementary steps towards understanding these numbers. So this one's particularly interesting because its proof primarily uses these quantum subgroups. It uses these commutative algebra objects to prove this result. So way up to the minute research, Terry and I looked at Frobenius-Perron dimensions in a paper last year and proved that the Frobenius-Perron dimensions of simple objects in the category, they live very close in a number-theoretic sense to the Frobenius-Perron dimension of the category itself. So, so this Frobenius-Perron dimension of the category sort of controls a lot about the number theory corresponding to the category. So for instance, if I look at the central charge, so for categories, we like to think of this in a multiplicative way rather than an additive way. But if we look at this order of this multiplicative central charge, which is some root of unity, then it's bounded by a function of the Frobenius-Perron dimension, or more specifically, the exponent of the Galois group of this field extension generated by the Frobenius-Perron dimension. So this one number, just one number out of all of these numbers that come out of the situation has a very tight control over what's going on. And lastly, in terms of these Witt group relations, in terms of the relation of these categories amongst quantum subgroup, we found that if you fix a field, so maybe Q adjoin square root of 7 or something like this, and I look at Witt classes whose unique representative has a Frobenius-Perron dimension which lies in that field, then this set of Witt equivalence classes is completely closed under tensoring, under the group operation. And so you get this nice lattice of subgroups that corresponds to dimension fields. And this essentially follows from a very simple fact, which is that this Frobenius-Perron dimension of these quantum subgroups, of these algebra objects, lies in this sort of base field of the category. So the list could go on and on and on about new results, because like I said, we still don't have this overarching understanding of what these dimensions are. So there's open questions everywhere as well. So for instance, we don't even know when the dimensions, the Frobenius-Perron dimensions of objects divide the dimension of the category itself. This is completely open. We don't even know how the categorical dimension and the Frobenius-Perron dimension, how they talk to each other. So which field does one sit inside the field generated by the other or not? Completely unknown. As I mentioned before, we don't know whether the categorical dimensions of these categories are discrete. Another thing that hasn't been done, so for instance, if you look at categories whose Frobenius-Perron dimension is an integer, you can find an example for every positive integer. But if you make the field that you're considering slightly larger, so maybe Q adjoin the square root of 2, we have no idea what the full characterization of numbers which are realized by the Frobenius-Perron dimensions of the categories is. Okay, so you can start making a list of them and crossing them off one by one, but there's no result that you have a full complete list of these numbers. So a more general question off of this is, does there exist some field which is sort of empty? So are these fields generated by dimensions all possible cyclotomic fields that you could imagine? Or can you find one where the only Frobenius-Perron or categorical dimensions have to be integers? So an example of why this might be an interesting question is that through mine and Terry's work on these WZW categories, we found that in fact, the fields generated by the global dimensions of these categories is very specific. So for all of these categories, for all the algebras, for all positive integers, with exactly 4 exceptions, so just 4 of these categories, all of these fields look like Q adjoin cosine of 2 pi over some positive integer. They're very boring categories as far as number theory goes. So for instance, you can't find an example of a category whose global dimension generates Q adjoin the square root of 7, for example. We just don't have any examples in the literature. So possibly this is one of these empty fields. We just don't know. So another reason why this might be reasonable is if you can prove, as I did, which is if you look at certain quadratic extensions, for example, Q adjoin the square root of 2,593, which is a prime number, not a random prime number, but it is prime, then the Frobenius-Perron dimension of the smallest possible category that could exist in that field has a size which is over 10 to the 48th power. So if you did find a category which has a dimension in this field, it would have to be just ridiculously massive in size. And you can go on in an infinite list of these, but I picked this next one because this one means your category has to have a dimension which is larger than, you know, the order of the monster group, for example. So it could be possible that the fields, not just the number themselves, but the fields that appear corresponding to these categories are incredibly restricted. We just don't have very many examples which allow us to, you know, explore this further. So if you, you know, mature slightly from, you know, grad school days and you're looking at dimensions and you start looking at other rows and columns of this modular data, then you immediately run into this fact, which is another fact from, you know, 30 years ago, which is that there's a nice Galwa action on the rows and the columns of this S matrix. So if I fix a modular tensor category, then I take any Galwa automorphism, which I've described it as this coming from this absolute Galois group, so I don't have to talk about which specific fields the S matrix generates. If I take one of these automorphisms, then there's a unique permutation of the simple objects given by the following rule, essentially that I look at how the Galois automorphism acts on the Verlinde eigenvalues, or how the Galois automorphism acts on characters of the Grothendieck ring. And so when I refer to the Galwa action, I am often just referring to the permutation of the simple objects that corresponds to this action. Okay. So one consequence of this is you can look at individual entries rather than looking at the Verlinde eigenvalues. And you can see that it almost works out that if I apply a Galois automorphism to an entry in the S matrix, I get the entry of the S matrix that corresponds to applying the permutation to one of the indices, but it's off by a sign, okay, because of these quotients. And so there's this sign function that comes along with this Galwa action, which is actually quite telling about these categories. So the big difference between my arguments about these quantum subgroups and Terry Gannon's general arguments is exactly this sign function. So if you look at the Galwa action, which takes the dimensions that I looked at, and look at how the Galwa action permutes, you know, this dimension row or column of the S matrix, this sign function gives you relations that have to be satisfied related to these quantum subgroups. And so this, I think crippling is the word that people usually use. This sort of cohesion of this sign function with this Galwa action is very restrictive, okay, when you look at these quantum subgroups. So this is something that comes up very naturally in this quantum subgroup problem as well. So moving forward, I've been thinking a lot about this Galwa action to understand the number theory that's involved with these categories better. And a lot of the literature about this Galwa action in particular, so not just studying Galwa actions for individual categories or specific cases, but just studying this Galwa action as a whole and trying to find new results about it is very recent. So for instance, just last year, there was a very nice paper that I'd like to advertise, which is looking at which modular tensor categories have a single Galois orbit of simple objects. They call these transitive categories. So this means that I can get to any other row or column in the S matrix by looking at the Galwa action of some automorphism. And it turns out that these are completely classifiable. So these are exactly huge products of SL2 theories where the order of the T matrix is a prime number. So the assumption that I didn't write down here is that all of these primes they're co-prime. There's no repetitive primes in these products. So these are exactly the categories where the Galwa action is sort of simple in the sense that you get everything in the category by looking at the orbit of just one object. And you can also look in the complete opposite direction. So you can sort of treat this as an exercise if you want, because it's a little bit easier, but you can ask for which categories is this Galwa action completely trivial. So what I mean by this is that every simple object is its own orbit. So they're all fixed points of this Galwa action for every automorphism out there. And you can actually find that these are classifiable as well. They look like what we call pointed categories. So I haven't used this notation before, but this is a category where all of the simple objects have dimension, Frobenius-Perron dimension 1. And so these all correspond to metric groups. And so you have an abelian group of the simple objects, which in this case must be an elementary abelian 2 group. And sort of all of the modular data that corresponds to this category comes from a non-degenerate quadratic form on this finite abelian group. So this is another complete classification by this Galwa action. So these are actually quite boring at the end of the day. So these numbers, this number theory that we've been talking about and that I've been advertising, very much constrains this Galwa action. They're very related. And you can see that by looking at these number fields, which are generated by the Verlinde eigenvalues. So if I fix a simple object, I can look at all of the eigenvalues or all of the numbers which appear in the character of the Grothendieck ring, which corresponds to that simple object. And it's very easy to show that the number of simple objects which are in the orbit of that simple object that you picked is exactly the degree of the field extension corresponding to this field. And so from a very number theoretical perspective, I can study this combinatorial fact about the Galois orbits. And you may want to look at something more general, which is just combining all of these fields together and looking at the field generated by all Verlinde eigenvalues. So these things were considered a long time ago, very long time ago, 1997. These were done by, I think, Gannon and Walton. I wrote it right here. Yeah, so Terry Gannon and Marion what's Walton's first name? Oh, I can't remember at the time. But
I think it's Mark. Is it Mark Walton?
Mark, is it?
I think so.
I thought it started with him. Yeah. So Mark Walton and Terry Gannon, they computed these fields of Verlinde eigenvalues explicitly for the type A categories, so for SLN. And they actually used what I would consider very sophisticated arguments, because a lot of the language that we have available to us now wasn't available at the time. So I don't mean to sound like a young kid, but I'd almost call them classical arguments. They seem slightly dated, but I say that with the utmost respect, because really a lot of the modern arguments were influenced by them. And so with our more modern arguments, so Terry and I in particularly, with our results on these Frobenius-Perron dimensions, we completely classified all these fields for all of these categories, which sounds like a task, but as you saw, these Frobenius-Perron dimension fields, these have a very specific form. And so it's not too large of a step to study the fields generated by the entire S matrix once you know these Frobenius-Perron dimension fields. So with this information, there's this nice open problem, which I'm surprised hasn't been considered a lot sooner, which is that once you know all of these fields, you can look at both the size of the Galois orbits, but also how many Galois orbits there are for each of these categories. There's a very nice geometric interpretation of what these Galois orbits are, which we'll see an example of on the next slide, that make the answers to these questions quite interesting. And you don't really see it until you compute a sufficient number of examples. A lot of these numbers seem quite random. So I think this is a very interesting problem to think about, and very approachable considering what we know now. So this brings me to sort of the final concept that I wanted to talk about, which came up while studying the relationship between these number fields and the Galwa action, which is a notion of Galois stability in these categories. So if you look back slightly, so this was only 5 years ago, and this might be something that was known before, but this was the only reference I could find to this fact, which is that if you look at categories for which the dimension column or row of the S matrix is fixed under the Galwa action, so every single Galwa automorphism fixes the row corresponding to the unit object, then these are exactly integral categories. So these are categories where the Frobenius-Perron dimension of every simple object is an integer. And so these categories are categories which are representation categories of Hopf algebras. So you have this very strong constraint about what types of categories come from this type of restricted Galwa action. Now, I kind of cringe when I read results about this, because this looks like something that should be more general, because it's something that's just about integral categories. And to me, the integral categories are what we want to generalize. So we don't want results about just integral things. We want results about arbitrary number fields. You want to be able to say, if the global dimension of C lies in this field, then you can say something very strong about the category. So I keep giving this formal warning that if someone writes a result like this, that the first instinct that I have is to go along and generalize it. And in this case, that's exactly what happens. So this is an example of a much more general phenomenon, which is the following, which I'll illustrate by an example. So if I look at the adjoint subcategory, so this is a very specific fusion subcategory of our modular tensor category corresponding to SO5 at level 4. This is also the trivial component in the universal grading of this category, for those of you who like that language. And I look at all of the Galois automorphisms or all of the non-trivial Galwa actions on this subcategory, then they're very nice in the sense that they preserve this fusion subcategory. So I stole this diagram from myself, and what's not illustrated is all of the simple objects in this category, which aren't in the adjoint category. So what you're seeing here is actually a strict subset of the simple objects, but you can see it acts in a nice, symmetrically pleasing way, but most importantly, it preserves the adjoint subcategory. So you can think of this as sort of the next step up from this fact about preserving the unit object. So one could call this fusion subcategory Galwan Variant. Maybe you call this containment of one fusion category inside of another as a Galwan Variant embedding. And in this particular case, this is a degenerately braided subcategory. So this is not a modular category in and of itself. I think its center is rep z mod 2. So it has a non-trivial set of transparent objects. So you keep doing this, you look at all these examples coming from quantum groups, and you find that this is actually what always occurs. So you want to make this into a definition in the obvious way. So if I have a fusion subcategory of a modular tensor category, then we call it a Galwan variant embedding if the Galwa action for the larger category fixes that subcategory. It's a very natural way to think about it. And since this appears in every single example that you could possibly find, almost every single example, you should be able to maybe classify these. And I did that last year. It's not very difficult. You might want to try it yourself if you know something about this type of a problem. But you can classify these very specifically as fusion subcategories in modular tensor categories such that their relative centralizer, so this is the set of simple objects or the fusion subcategory generated by those objects which centralize, which commute very nicely with that subcategory, is integral. Okay? So the relative centralizer of this fusion subcategory is integral if and only if it's Galwan variant. Okay? So you actually have a very nice way of measuring whether this happens or not. So looking at a set of examples, well, going from our first example, if you have some sort of what we call a graded extension, so you look at the adjoint subcategory of any modular tensor category sitting inside its parent, then this is an example of a Galwan variant embedding because the centralizer of the adjoint subcategory is exactly the set of pointed or invertible objects of that category, which is an integral subcategory. So adjoint subcategories are always Galwan variant. If you look at the quantum group categories, we actually have a nice classification of all fusion subcategories of every single one of these categories, which is due to Stephen Savine. And you find that all of these categories which aren't pointed are Galwan variant. Okay? Basically, every single fusion subcategory in these WZW categories is either pointed or it's a centralizer of a pointed subcategory, except at level 2, where there's a few exceptions. So if you look a little bit further in generality, you can look at what's called a minimal modular extension. So these are, if I take something which isn't necessarily modular, and I look for the smallest possible modular category that I can embed this inside, which I'll make explicit in the next slide, every single one of these minimal modular extensions is an example of a Galwan variant embedding. And there's lots of literature about these types of embeddings as well. And lastly, if I take something which is already integral, so I take some representation category, some Hopf algebra, and I embed it in its Grunfeld center, then there's this very nice fact that the centralizer of that category in the center is its reverse category. And so I have the exact same dimensions. And so I satisfy this criteria for being Galwan variant. So every integral category, for every integral category, there exists some Galwan variant embedding for it. And so all the examples that we know of, and even more generally, things that we don't have a complete grasp on understanding, these are all examples of this phenomenon. So in the interest of time, I think we're sort of approaching it. I'll end with this next slide, which I think is a good place to stop, which is sort of an interpolated conjecture. So there's an old conjecture about these minimal modular extensions. And the definition of these is contained in this statement. So we know exactly what the dimension of a minimal modular extension should be. And the conjecture was that for every, maybe degenerately braided fusion category or pre-modular category, then there exists some modular category that it sits inside of that exact minimal possible dimension. And this was proven to be false. I don't know how quickly. It's actually very hard to find explicit examples of this written down, but there are lots of examples of this being false. There just simply aren't modular extensions that are that small for each category. So we have a conjecture that's completely false, and we have a conjecture that's completely true. So we'll call it a theorem, which is that there always exists some modular category containing any pre-modular category that you find. And that is simply its center. Okay? So every pre-modular category sits inside its center as a subcategory. But that's obviously much less restrictive. And the problem with this embedding, which is the embedding that a lot of people use to study things which aren't modular, is that these centers are sometimes disgustingly huge. We don't have a grasp on how, for instance, the rank grows when you consider these centers. Sometimes these centers are just absolutely massive compared to the original categories that you're looking at. And so in a perfect world, we would have some other way of embedding our categories into something modular that wasn't too disgusting, that had some control over the structure of the modular tensor category that we're looking at. And sort of this conjecture in the middle, hopefully, is some average of these two. And I put my name on it just so we know who to blame when it's inevitably false. But it's a good goal to work towards, I think, is to find an example where this conjecture is false, that if I take some degenerately braided category, so some pre-modular category, then there exists some Galois invariant embedding of that. So rather than passing to the center, I can pass to the center for integral categories, but for more complicated categories, hopefully there's a way that I can study just general braided fusion categories, we'll say, by embedding them into a modular tensor category, which is not too disgusting, which retains sort of some of the character of the original category that I started with. So in a completely naive way, you can think of, we have an S matrix for these degenerately braided things, and the only difference between that and a modular tensor category is that some of the rows or columns are linearly dependent. So it's not an invertible matrix. And passing to this Galwan variant embedding, if it exists for all these categories, is essentially just sort of padding the S matrix of the thing that you were looking at with enough numbers to be able to differentiate the columns of this degenerate S matrix. And so obviously this isn't how you want to go about proving something like this, but it's kind of feasible when you think about it in that way. Whether it's possible in general, hopefully that will be the topic of a future talk. But yeah, so in the interest of time, I think I'll stop there.
Okay, thanks very much for that beautiful talk.
Thank you.
I'll